Welcome to section 5.5. We are going to be looking at the substitution rule. Okay, so we've been looking at integration, and we saw, believe it or not, some relatively straightforward integrals. And now let's consider something like this. The integral of 2x times the cosine of 3 plus x squared dx. All right, well, we would have to find the antiderivative of this integrand, right? And if you look at this, it's a product, which is a little bit difficult, and we're using a chain rule as well. So how are we going to do this? Well, let's approach it like this. Because there's so much involved here, because there's a product, because there's a chain rule, what we're going to do is we're going to do some clever substitutions, okay? Because there's a lot going on in this integrand. So I'm looking at this integrand and I'm thinking what I know about taking derivatives and such. And I'm going to focus on the argument of cosine. And I'm going to say, let's let u equal 3 plus x squared. Okay? And we know that as far as, integration, finding the derivative and integrating are inverse functions or inverse processes. So I'm going to look at du. So I'm going to take the derivative essentially of u with respect to x. And what do we end up with? We end up with 2x, okay? All right, so that's taking the derivative. I'm going to do a little bit of magic because this is our thought process right here. We have just made that as a substitute of u, right? And now, if we're substituting in u, notice we have two places that contain x. We have it right here for dx, and we have it in the integrand as well, okay? So what we're going to do is we're going to substitute dx with du by multiplying both sides by dx. So we really get that du is 2x times dx, okay? And now all of our substitution is complete. We can completely rewrite this integrand in terms of u. All right, and I'll show you how. I'm going to color coordinate because I love that. And I'm going to rearrange some things. I'm going to put the 2x by the dx. Do you see how I did that? Okay, and now these are the substitutions. U is 3 plus x squared. So I'm going to rewrite that in terms of u. So it's going to turn into the cosine of u. And then 2x dx, we're saying that that is du. Okay? And now we have the whole thing in terms of u. And so now actually we can find the integral of the cosine of u du. Okay? What's the antiderivative of cosine? It's sine. And we're just going to focus on the indefinite integral for now. So when it's indefinite integral, what do we have to add? Plus c. Okay? And there's actually one more step because we started with something in terms of x, and now we have something in terms of u. So that's just bad manners. So we want to start with this or end with the same variable we started with. So we're going to resubstitute that u is 3 plus x. Whoops, 3 plus x squared. And then plus c. And there you go. So it's a new fancy way of taking the integral. And remember, you can always check your work by taking the derivative of what you found out, right? So if we took this derivative, it's the chain rule, so it'd be cosine 3 plus x squared times the derivative of the inside function, which is 2x, which is exactly where we started, okay? All right, so that rule is called the substitution rule. So the substitution rule says this. So for u equal to a function of x, okay, if we have a composition of functions, whoops, like this, all right, we can make the substitution with u. And honestly, the rule in general looks a little bit more confusing than what we actually do. I think it's a little bit easier in practice. All right, but that's our substitution rule. Let's practice it. Okay, so we would want to find, let's say the, indefinite integral still, we'll just do indefinite for now, of x cosine of 3 plus x squared dx. It's familiar, right? Last time it was almost the same thing, but we don't have the 2. So let's see how that's going to look. Okay, so again, when we come in, remember when we integrate, we don't know what rule to use. We don't know what strategy. We have to be critical thinkers. And looking at this, I don't know a function whose derivative is x cosine of 3 plus x squared off the top of my head. All right, but I do see some composition of functions, cosine of 3 plus x squared. So that's telling me maybe I should use a substitution and substitute that inside function. Okay, so that's my thought process. And then when we take the derivative of both sides, some people like to write out this whole step du dx is equal to 2x, but I just like to write du and then 2x dx because I've done it enough times, but you can definitely throw in that intermediate step, right? And that intermediate step is to write it more properly, right? This is the proper way to write it, and how I did it was a shortcut. So you could put that step right there. It doesn't matter. Okay, so once you figured out your u substitution and you find the derivative, then you go back to your function, okay? And you kind of start checking off boxes. So we got rid of this. That's going to become u. And now we have an x dx. So we have to match x dx to something in terms of du. And right now we have 2x dx. So our expression, our integrand, is actually x dx. So what can we do to get x dx all by itself? We can divide by 2. All right, so that's the substitution we're going to be using. So let's rewrite it. We're going to bring all this information back. We have this. I'm going to put the x by the dx. Okay, and now it's time to make all of our clever substitutions. We said 3 plus x squared is u. And we said x dx is 1/2 du. All right, and then we just kind of take a step back and notice all the x's have disappeared, and we just have things in terms of u. So that's important. Make sure we just have u's. All right, and now this 1/2 is just a factor that's a constant. So if it's easier, let's just put that on the outside of the integration symbol, and we can worry about it later. So now the integral of cosine of u is sine of u. And since it's an indefinite integral, what do we need? Plus c. And then what's our final step? If we started with x's, we have to end with x's. So u is 3 plus x squared. All right, and there you go. And remember, you can always check your work once you have your final answer. You can always check it by doing the opposite process, which is taking the derivative and seeing if it gets you back to where you started. Okay, let's look at some more examples. Okay, so integration of dx divided by 4 minus 7x, okay? Okay, so, again, same thing. We don't really know offhand what this integration could be. I do notice we have an x down here, okay? And so this kind of reminds me of 1 over x, right? And so I can think of this as a composition of functions. So I'm looking at that denominator, and I'm going to let u be that denominator. Okay, so that would take care of this bottom part, the denominator. But I have this dx, so let's see what happens when we take the derivative. Be du be 0 minus 7 dx. All right, well, there's the dx I want to get rid of. And here it is over here. So what can we do to get dx to be all by itself? We can divide out by negative 7. Okay, so you see how we always have to refer back to the original integral when we're doing the substitution? Okay, so according to our substitutions, dx becomes negative 1 over 7 du, and 4 minus 7x is going to be substituted for u. And now this is much more manageable. I'm going to bring that constant factor in front of the integral sign. And again, we know how to take the integral of, du over u, or 1 over u. That's the natural logarithm. Okay, and then since it's an indefinite integral, we're going to add that plus c. And then what do we need? Since we started with x's, we have to end with x's. So it looks a little sloppy. All right, so there you go. Okay, let's look at another example. Let's say we wanted to take the integral of sine of x times sine of cosine of x dx. All right. Well, remember, when we're doing our substitution rule, figuring out what we have to substitute is sometimes tricky, okay? Sometimes it's helpful to see if there's any inside functions. And so looking at this integrand, do we spot an inside function, like a composition of functions? And this cosine of x is behaving like an inside function. So I'm going to start with that. I'm going to let u is equal to cosine of x. Then same thing as before, let's take the derivative of both sides. I'll throw on the extra step just to switch it up. So derivative of u with respect to x, negative sine x, and then you multiply by dx. All right, then let's take a step back. Let's go back to our original integrand, and we'll kind of start checking off our boxes. Cosine of x is going to become u, and then we have sine x dx. And over here we have negative sine x dx. So what do we have to do? We have to switch that negative, or multiply both sides by negative 1. All right, and then now we're ready for substitution. So if you would like, you can always rearrange the factors to really help with the substitution, but it's not a criteria. You don't have to do that. All right, and then what do we have? We have that sine of the cosine of x is going to become the sine of u. And then sine x dx becomes negative du. And now we're ready. Oh, actually, before we do that, let me bring that negative to the outside. If you want, and I want. Okay, and now what's the integral of sine? Well, I guess if we left the negative there, that would have been fine too. But it cancels out either way. So the derivative of negative cosine is positive sine. Minus minus will become plus. And then because it's indefinite, we add that plus c. All right, because we started with x's, we end with x's. So let's make sure we rewrite this as cosine of x plus c. And remember, how do we check it? We can always take the derivative as our final check. Okay. Well, here we go. Let's look at another example. And why don't you guys try this one on your own now that we've done a couple. Let's do the indefinite integral of sine root x divided by root x dx. All right, so go ahead and push pause, work it out, and then come back and we'll see how you do. Okay, so it's helpful to find your u to look for an inside function, like a composition of function. And I see that the root x is the argument of sine. So I'm going to try that out. All right, so x to the 1/2. And then let's take the derivative. I forgot to write the dx. That's in the middle part, but there you go. All right, and it's looking hopeful because we have a square root of x in the denominator. So that's lovely. So to get it all by itself, what did you guys do? You multiplied by 2. Good. All right, so if you wanted to rewrite this so you could clearly see how you're substituting, you can pull that 1 over root x out of the denominator and into its own little fraction. And then we see we have this. So sine of root x, we said, was u. And then 1 over root x dx is 2 du. Okay, and I'm going to move that 2 in front. So now this becomes our integral, which is a little bit easier to handle than the one we had before. All right, so what's the integral of sine? We just did that one. We'll do it again. And because it's an indefinite integral, you guys did the plus c. And then your final step is to return the same variable you started with. So root x. Okay. Good. So let's look at an example that's a little bit different. Okay, so let's say we're looking at the square root of x times x plus 2 dx. And we can see that... You're back, thank you. We can see that we have a composition of functions, right? The square root of x plus 2. So let's start off with that. And we'll let u be equal to x plus 2, that inside function. And so that will take care of this. But notice when we take the derivative the derivative of x is just 1. So it's a straight substitution. du is just going to be dx. All right, so this is what we have. So x plus 2 is u, and we just said that dx is du. But what's the problem? We still have an x, so we're not done. So this was a little bit different. So what can we do? Well, let's look at our scratch work over here. And I see an x, right there. So I can get x in terms of u. I can subtract 2 from both sides, and x is going to be u minus 2. So I'm going to make the substitution like that, which is a little different. Okay? All right, so let's see what we can do with this information now. Let's get rid of this product, and we can get rid of the product by multiplication, or excuse me, distribution. And notice the reason why we're able to distribute like that so easily, we don't have to do anything weird. There's no composition of function here. There's no compositions of functions. So that's one way of figuring out what technique to use. You know, we can just straight up multiply. We don't have to do anything fancy. All right, u times u to the 1/2. You can add the exponents. Okay. All right, that's not so bad. And then we can take the derivative. The integral, I mean. So on the u, let's add 1. And then flip the exponent for the coefficient. And then same with this u. 1/2 plus 1 is 3/2. And then the new coefficient, we flip the exponent. And then, of course, plus c. And then final step, we're going to resubstitute back. And we said that u was x plus 2. All right, 2 times 2 is 4. And then finally we have the plus c. All right, and then there you go. So then that would be your solution for that one. So a little bit different. It's another technique. Okay, let's do another example. And I like this example because it highlights that sometimes, again, when we take the integral, we don't know which path to take or what technique to use. Again, taking the derivative, the rules are set. You're just going down, once you figure out what path to go on, you just go down it. But in this case, you know, we see we have a quotient. It's really hard to take the antiderivative of quotients and products, as we know. So there has to be another solution. So that kind of tells us to do the substitution rule. All right, and now the question is, what could the inside function be? What could the inside function be? All right, so maybe we think of the inside function as the denominator. Okay, and then we take the derivative. Okay, and we go back to the original function, and we need an x cubed to make a substitution for u. We need an x cubed, and notice we just have an x. We are not allowed to divide both sides by x squared, 4x squared. So we get the x dx here, right? So x dx, we can make a substitution. But if we make that substitution, we still have an x in there. So that's not going to work. So we're definitely not allowed to do that. So I'm just going to cross it off. Cross it off. This is not allowed, ever. We have to end up only with u, no old variables allowed. And that also tells us that this substitution is wrong. Because we needed to end up with something like x dx, and we got x cubed dx. Substitution is wrong. Okay, so let's do something else. Well, we know whatever our u substitution is, when we take the derivative, we have to end up with x. So that's telling us that maybe we should try what power for u? Maybe we could try x squared. All right, so now in this case, the composition function would be, an x squared right there. X squared squared is x to the fourth. And kind of reverse engineering that, why we're doing that is because now we have that x dx, and we can actually substitute the u. All right, let's get rid of that 2. Divide both sides by 2. And now we have a substitution we can work with. Okay, so we had to be clever on that one. Okay, so again, what did we decide? We decided that x dx becomes 1/2 du. And then on the bottom, 1 plus x to the fourth. Well, we're saying u is x squared. So x squared squared is x to the fourth, right? And just a little side note. Oh, let me do a blue color. X squared. How do I want to do this? So we have, I just said it was u squared, which is x squared squared, which is x to the fourth. Okay, so that's how we're going from x to the fourth to u squared. All right, and then let's bring that 1/2 out front. And we're looking at this. And does that integral look familiar? So what function has the derivative of 1 over 1 plus u squared? The inverse tangent. All right, and then plus some constant c. Okay, and then, while we're stopped here, let me just, let me point this out in case you were wondering. It's really 1/2 plus some constant. Excuse me, 1/2, the antiderivative plus a constant. But I never write in these parentheses, and I'll tell you why. If we were to distribute the 1/2, we get the 1/2 inverse tangent of u. And then 1/2 times a constant, guess what? It's still a constant. I can still call that c. I'm not saying what c is. All I'm saying is c is some constant, whether it's 1/2 times the constant or just a constant. It's a constant no matter how you slice it. That's kind of exciting. All right, so then what's your u? We said it was 1 plus x to the fourth, and then plus the c. Oh, sorry guys. I was looking in the wrong place. I was looking up here, but I have right there, it's the wrong substitution. It's really x squared. Much better. All right, and remember, you can always check by taking the derivative. Okay, so that's the indefinite integral. In part 2, we're going to be looking at the definite integral using the substitution rule.